n is in second, and we can replace Sn minus 1 with u n minus 1 plus half a into n minus 1 whole square. So finally we get Sn is equal to u plus 1 by 2 a into 2n minus 1. Now a word of caution: whatever equation that we have just discussed, they are valid only for constant acceleration, and all those equations are vector equations, though we can also use them for motion in one dimension, that is when a particle travels along a straight line, and we can decide either to or fro direction to be positive, and accordingly we can decide the sign of various quantity. For example, if a particle is traveling along a straight line from A to B with some velocity u, so we can decide that the direction from A to B, that is this direction, is positive, and the direction from B to A is negative. So accordingly we can say that the particle has positive velocity. Suppose there is another particle which is traveling from point B to point A with velocity v, so the velocity of this particle will be negative. Similarly, if the acceleration is in the direction from A to B, it will be positive, and if the acceleration is in direction B to A, it will be negative. So even though the equation that we have discussed are vector equations, we can use them for the motion in one dimension after we have taken care of sign. Now let's have a look at another displacement time graph. So here we can see that the slope of ST curve is decreasing, that is displacement time curve, it is decreasing. So this is the case of deceleration. Also there is a point on the curve where the slope of the graph is 0. This is that point, and since the slope of the graph is equal to the velocity of the particle, so oh man, it sucks. Now let's talk about displacement time graph. In displacement time graph, the displacement of particle is plotted against time. Generally we take displacement along y-axis and time is taken along x-axis. So first let's see a typical displacement time graph. So here, as you can see, the displacement is being taken along y-axis and the time is being taken along x-axis. Suppose this point is S1 and this point is S2, so S1 S2 is the actual graph, and which is a straight line, and this straight line makes an angle theta with the horizontal, so the slope of the straight line is nothing but tan theta. Since this slope is constant for the whole graph, that if we want to take the slope of the graph at any instant, it is same as tan theta. So here we have a constant slope graph, so which indicates that the velocity is also constant, since velocity is given by dx by dt, and dx by dt is nothing but the slope of the displacement time graph. So if the slope is constant, it means that velocity is constant. So whenever the displacement time graph is a straight line, it would imply that its slope is constant, which would imply that its velocity is constant. Now let's have a look at a displacement time graph where the graph is not a straight line. So here, as you can see, that the graph between displacement and time is not a straight line, and so its slope is also not constant. So if the slope is not constant, it means that the velocity is changing, the velocity is not uniform. So we can write that if slope is not constant, it means that velocity is not uniform, which will imply that there is some acceleration or deceleration. So in this particular graph we can see that the slope of the graph is increasing with the time. So the slope of the graph is nothing but ds by dt, which is our velocity. So here we can see that the slope of the graph is increasing with time, which means that the velocity is increasing with time. So here we have a case of acceleration. Now let's have a look at another displacement time graph. So here we can see that the slope of displacement time graph is decreasing with time. So this is the case of deceleration. Also there is a point on this curve where the slope is 0. This is that point. And since the slope of displacement time curve is nothing but the velocity of the particle, so this is the point where the velocity of particle becomes 0, and after this point the velocity of the particle changes direction. So if you want to interpret this graph, so let's say that at time t is equal to 0 the velocity was v1, and because of deceleration this velocity keeps decreasing until it reaches the value 0, and after that the velocity of the particle changes direction. Now let's have a look at distance time graph. Distance time graph is a graph between distance traveled by the particle and the time. This graph is always monotonically increasing since the distance traveled by the particle cannot decrease with respect to the time. So there are some similarities between displacement time graph and distance time graph. Till the magnitude of displacement is increasing with time, distance time graph also follows displacement time graph. When the magnitude of displacement starts decreasing, the distance time graph still increases, and it is actually the mirror image of displacement time graph along the time axis. Also the slope of distance time graph will give you the instantaneous speed. Now let's have a look at a typical distance time graph. Now we'll take the same displacement time graph and we'll see how we can get the distance time graph from it. So as we have already seen that the velocity becomes 0 at this point. So since the displacement is increasing with time from point A to point B, point B is the point where velocity becomes 0. So from point A to point B, the distance time graph will resemble the displacement time graph, and from point B onwards it will be the mirror image of displacement time graph along the time axis. So this is our time axis. So from point B onwards the distance time graph will be nothing but the mirror image of displacement time graph. That is something like this. Since the distance traveled by the particle cannot decrease, it will always increase. So this is why the distance time graph is always a monotonically increasing graph. So this is all about our distance time graph. Now let's have a look at velocity time graph. Velocity time graph is the graph between velocity of a particle and the time. The slope of this graph at any given point will give us instantaneous acceleration at that point of time, and the area under the graph in a particular duration gives the total displacement in that particular duration. So now let's see a typical velocity time graph. So from here we can see that at time t is equal to t1 the velocity is v1, and at time t is equal to t2 the velocity is v2. So the total displacement by the particle between time t1 and t2 will be given as the area under the graph between time interval t1 and t2. So this is the total area. So this is nothing but the displacement of the particle. Also, the slope of this graph at any given point will give the value of instantaneous acceleration. So now we can say that if the velocity time graph is uniform, that is a straight line, suppose this is velocity time graph, so here the slope is constant, which means that acceleration is also constant. Here since the graph is not a straight line, it means that the acceleration is varying with time. Similarly, we can have acceleration time graph also. This is a graph plotted between acceleration of particle against time, and the area below the acceleration time graph gives change in velocity. Now let's see the vector form of equations of motion. So first we'll see the equation v is equal to u plus at. So this can be think of as, suppose this is a vector u and this is a vector at. So this will be our vector v, which is equal to u plus at. Similarly, displacement is equal to ut plus half at square. So again we can think of it as, suppose this is ut, here u is vector and t is scalar, so this is the case of a scalar being multiplied to a vector quantity, and this is half at square. So this will be our displacement vector, that is s, which is equal to ut plus half at square. Similarly, we had equation v square is equal to u square plus 2as. We can think of it as dot product of v into v, which will be equal to u dot u plus 2 into a dot s. So here all the three terms are scalar. So in this way we can visualize the equation that we have derived earlier in their vector form. Now let's see the equation of motion when initial velocity is 0. So here the value of u is 0, which means that particle is at rest initially. So if in the equation v is equal to u plus at, we put the value of u as 0, we'll get v is equal to at. Similarly, in the equation s is equal to ut plus half at square, if we put u is equal to 0, we'll get s is equal to half at square. And in the equation v square is equal to u square plus 2as, if we put u is equal to 0, we'll get v square is equal to 2as.